Hi everyone, my name is Nadya, and in this video I will demonstrate how to solve the given initial value problem using Euler's method, and I will also explain the concept of Euler's method and derive its formula, and then demonstrate the solution using Microsoft Excel, and then finally compare the approximate solution with the exact solution by calculating the approximation error.
Euler's method is a numerical method used to approximate the solution of an initial value problem. An initial value problem consists of a differential equation together with an initial condition. In this question, the differential equation is dy dx equals to x squared plus 2 over y, and the initial condition is y bracket 0 equals to 1. Now, looking at this diagram, you can see that the curved line represents the exact solution of the differential equation, while the straight line is the tangent line at the known point, which is xn, yn. The differential equation provides a slope of this tangent line, which is f bracket xn, yn. We move a small horizontal distance called step size, which is denoted by h, from xn to xn plus 1. So instead of following the exact curve, Euler's method follows the tangent line. By repeating this process, we can approximate the solution over the interval. So now, moving to the derivation of the Euler's formula, the Euler formula is derived from the differential equation of dy dx equals to f bracket xy. The derivative can be approximated using finite differences as yn plus 1 minus yn divided by xn plus 1 minus xn. And as you can see from the diagram above here, xn plus 1 minus xn is h, so we can just replace it, giving you yn plus 1 minus yn divided by h. After that, we multiply both sides by h, giving you yn plus 1 minus yn equals h f bracket xn yn. Then, rearranging the equation, we can obtain the Euler's method formula. I will now demonstrate how Euler's method is implemented using Microsoft Excel. Since the question does not specify a step size, I choose my step size to be 0.2, and this divides the interval from x equals to 0 to x equals to 1 into 5 equal steps. So for the 0 step, I plug in the initial condition, which you can see here. When x equals to 0, y is equals to 1, so I put it here. And then for this f bracket x, y, I just sub in the x and y values into this equation to get my slope. And this slope number is used to determine the next value of y, which you can see here in the Euler's formula. This is the slope number. So the next step is step 1. The next x value would be the previous x plus 0.2, since as you can see here, the next value of x is the previous x plus the step number, and this is continued all the way until x is equals to 1. And then for the y values, as you can see here, the previous y, which is 1, plus 0.2, which is step size, times the slope number, which is 2. And this continues until x is equals to 1. So therefore, when x equals to 1, our y value is 2.430454. Finally, I will compare this approximation with the exact solution. So how do we find for the exact solution? The first step is to solve the differential equation. This is done so by separating the variables and integrating them both sides to get your general solution. And then we apply the initial condition, which is when x equals to 0, y will be equal to 1. So we sub it into the general solution to get your c equals to 1. Hence, we will find our formula to find the exact solution. So step 2 is finding exact value when x is equals to 1. So we can sub in x equals to 1 into the equation to get y value of 2.380476. And then step 3, we'll get to compare with the Euler's approximation. And then after comparing, step 4, we calculate the approximation error, which is by subtracting the Euler's approximation with the exact solution to get the absolute error of 0.049978. And then we can find the percentage error, which is dividing the absolute error with the exact solution times 100, which would give us about 2.10%. Therefore, this difference occurs because Euler's method assumes that the slope remains constant over each interval, and using a smaller step size will produce more accurate approximation.
In conclusion, the Euler's method is a simple and systematic approach for approximating the solution of differential equations, and using a step size of 0.2, I obtained an approximate value that was close to the exact solution with only a small percentage error. Hence, this demonstrates that Euler's method is an effective numerical technique for solving initial value problems. Thank you for your attention.